It's my pleasure to introduce Ioana Coman from IPMU, talking about modularity and resurgence on topological free manifold invariants.
Thank you. So thank you very much for the invitation. I guess this talk is based on a paper that came out earlier this year, this spring. And I guess the topic is quite well suited for the seminar series since it deals with quantum field theories, modularity, and there's a resurgent component involved. So the main player in this story that I want to talk to you about is they are Q series of this form. What is a defining property of them, or a main characteristic, is that they have this nice integrality where they have integer coefficients and integer powers, and they are convergent Q-series expansions inside of the unit disk, maybe a modular finite set of points. And what they represent is they represent counting functions. Now, what it is that they count, this depends on the perspective that one takes, because they have entered, since they were introduced, they have entered in different related areas of research. And for example, one thing that they have that makes them special is that from a number theory point of view, they are examples of quantum modular forms. So they are not invariant under modular transformations, but still their transformation is somehow well behaved. Now, where they enter from the point of view of three-dimensional supersymmetric quantum field theory, where they get identified with a half index. Under a 3D correspondence, they are also identified with topological invariants of an auxiliary three-dimensional manifold. And experimentally, given their definition, they have been identified with characters of vertex operator algebras. So I want to review how these Q series, how they are defined, how they enter each of these topics, because one aspect that has been rather thorny and challenging was to go to the other side, as it's called. So to continue from inside of the unit disk to continue Q outside of the unit disk. And there are two main approaches for doing this. One is based on resurgence analysis, and the other one uses the modular structure of these functions. So to get here, I want to first spend a few minutes to review the broad background and setting, how these functions enter in the different areas, how they are defined, and where the limitations are. So first of all, from the point of three-dimensional supersymmetric quantum field theories, here, if we start actually in string theory with a stack of M5 branes, well, in M theory, and perform a twisted compactification on a three-dimensional manifold, then the resulting, in the remaining 3 dimensions, there will be a three-dimensional supersymmetric quantum field theory. And here, when the background is in this shape of a cigar, of a twisted circle vibration over a disk, the partition function of this 3D SQFT is called a half index. And it effectively gets expanded into a Q series, where the coefficients count the dimensions of vector spaces of BPS states. And because there is a boundary, there are boundary conditions that have to be specified. So the resulting Q series get indexed by this boundary condition. So we get this type of Q series expansion. And Q is related to tau, the complex structure of the boundary torus for the three-dimensional spacetime, by exponentiation. And from this 3D perspective, the 3D correspondence, the partition function on one side gets identified with a topological invariant of the auxiliary three-dimensional manifold. So these are the WRT invariants. Now, the physics perspective predicts a form for this partition function as an integral, which receives a contribution from the boundary and some contribution from the bulk. But now, the issue here is that supersymmetry localization also needs Lagrangian description to be available, which may not always be the case. So the 3D SQFT point of view does not really lead to a computational algorithm for these Q series. Now, if we then look on the other side, from the perspective of the auxiliary three-dimensional manifold and from 3D topology, then we start with the WRT invariants, because these were, well, the old story goes back more than 30 years at this point, where these invariants were introduced from two perspectives. So from one perspective, they are partition functions of 3D Chern-Simons gauge theory on the background at integer shifted Chern-Simons level. And from the other perspective, the definition given by Reshetikhin and Turaev uses quantum groups and link invariants, and they produce the invariant that I call here Z. And now this invariant, it admits a perturbative expansion around a saddle point of this action, which is an abelian flat connection, where the coefficients here, from a physics point of view, they can be computed perturbatively using Feynman diagrams. Now, the new story here with the Q series invariants that have been introduced, well, the motivation for proposing these Q series is twofold. On one hand, they are proposed as a non-perturbative formulation for 3D complex Chern-Simons theory that give a non-perturbative completion of perturbative expansions. And the second reason why they were introduced, they're introduced to categorify the numerical WRT invariants, where the categorification refers to replacing these numerical invariants with vector spaces. So in the resulting Q series, the coefficients are the dimensions of these vector spaces, and the physical perspective that I mentioned previously, these give an intuition for what these vector spaces are, and they are vector spaces of BPS states. Now the relation between the two sides goes through this radial limit in Q, which is the same as taking tau from the upper half plane to some rational point. So starting from the invariants that I have just introduced, taking this radial limit and summing over the labels that parameterize them produces the WRT invariants. So effectively, to go in the other direction, one starts with the perturbative expansions, performs a Borel resummation, and then a subsequent linear transformation that gives what are called the Z-hat invariants. So and now,
Ioana, sorry, there's a question.
I have a question. The Z-hat is defined for which group in your slide? SL2C?
It's always, so the Chern-Simons theory that I started with is SU2, and continuation assumes that it goes to SL2C. But really, when in this paper in 2016, the authors were picking a half-dimensional subspace when considering the flat connections. So initially it is just the SU2, and I'm very, very sketchy when I actually introduce and define how these functions are specified, it will be for A1 groups. Is that okay?
More or less. So your Q is the root of unity or what?
No,
Okay.
that's exactly the point. That is precisely it. So we started with just rational points, so 1 over k, or more general, there have been other papers that go to other rational points. And the point is really that the z hat invariants are defined in the upper half plane. So there is this continuation.
Thank you.
Okay. So now the reason why I said I threw in the non-perturbative is the fact that having performed this analysis, the group of Sergei Gukov said that there is this decomposition into the contributions from abelian flat connections. Imagine that the sum, that this bracket is not here, and that I'm putting an S here. I just realized a typo. The broad idea is that we have started with series that are specified by abelian flat connections, or equivalently there will be spin-free structures, but the resummed result decomposes into a contribution from abelian flat connections and the non-abelian flat connections that come from trans series. And now, to say a bit towards about the computational methods, because I've already said the physics point of view doesn't go too far. From 3D topology, there is the resurgence calculation. That is one approach. There is also a combinatorial algorithm that was proposed for closed three-dimensional manifolds and also for knot complements, that is based on the combinatorial structure of these manifolds. So for knot complements, this is a generalization, a two-parameter generalization of the Z-hat invariant, which was defined from an analytic continuation of the Jones polynomial, and which then allowed a number of connections to be discovered related to inverted Habira series of knots, to quantum group computations in terms of an R matrix, to Humphrey-P polynomials, and here the list goes on.
Now I will...
Sorry?
The knot complement, this construction of FK, it's for all type of knot, or you have the distinction between hyperbolic or torus or something like that?
No. There's here, I also said with conditions, because there's always this, I will show this on the next slide. There's always a fine print on how, what conditions need to be imposed such that the Q series that are defined are convergent Q series with Q inside the unit disk. So this is one of the thorny issues that I mentioned.
Okay.
So now to review, just for plumbed three manifolds, where how these to tell you what the combinatorial definition is. The simplest type of manifolds are the plumbed three manifolds, which are specified by a plumbing graph. So defined by a set of vertices, edges, and weights associated to each of the vertices, where given a plumbing graph, this is equivalent to a diagram of connected links. And the tree manifold is constructed by dense surgery on those links with framing specified by this integer. So now all of this data is equivalently encoded in this adjacency matrix where the weights enter the diagonal, and the other entries are 0 if two links are not connected, and 1 if they are connected. And one type of manifold that fits into this class are the cipher manifolds, the cipher fibrations over a two-sphere, which are defined by the cipher invariants. Now these are rational numbers, and the relation between these rational numbers and the weights associated to the corresponding leg of the plumbing graph is just given by a continuous fraction. And then a special type of these are the Briskin spheres, which are particularly nice because their adjacency matrix is unimodular, and they can be specified by 3 relatively coprime numbers, And the example that I will always use explicitly in the talk is what is called sigma 237, which has a very simple plumbing graph. And it's very illustrative for all of the structures that appear in these invariants. Now, what I mentioned earlier, what is the fine print, is that not all of these tree manifolds are okay to be considered for the definition. They must be weakly negative, which means imposing the restriction on the inverse of the adjacency matrix to be negative definite on the subspace that is related to the degree 3 or greater vertices. So what you see here is this entry is negative. Now the combinatorial algorithm, what was introduced in these papers that are now almost 8 years old, it specifies the z-hat invariant. So here I mentioned for A1 groups as a contour integral, which takes as input the adjacency matrix that enters through a lattice theta function and integrates over the parameters z associated to each node of the plumbing graph. And the result, in the case of sigma 237, going through this procedure with the adjacency matrix from the previous slide, one finds that the result is proportional to a linear combination of false theta functions. And these are one of the most simple examples of quantum modular forms. Now, what you see here is an explicit example, so expanded as a Q series. What has been shown for general negative definite cipher tree manifolds with plumbing graphs that have 3 exceptional fibers is that the z-hat invariant is in the span of false theta functions, where the index M is specified strictly by the tree manifold. So they all have what I'm highlighting here. They all have the same index equal to 42, and this is not a coincidence that it is related to the 3 relatively co-prime integers that specify the tree manifold. So having said this, a set of observations and questions that arise is that the z-hat invariants, they always appear not proportional to just one false theta function, but there's always a linear combination. So this hints to the fact that there is a hidden modular symmetry at play. So a question is, what does this actually imply for the definition of the invariants? Now, part 2, what I said in the beginning is that the invariant is defined for tau in the upper half plane. So one of the main questions is how to go to the other side, how to perform this analytic continuation. And moreover, what I have not yet shown, but I can state it just as a fact here, is that these invariants have been related to characters of modules of logarithmic vertex operator algebras. So on the wish list would be not to find just a function or a Q series on the other side, but to really find also a corresponding vertex operator algebra connection. So what I want to say today is then, in order to answer the first question, this hidden modular symmetry is related to vowel representations of the metaplectic group of SL2Z. And this hidden symmetry motivated us in the paper from the spring to generalize as defect invariants by introducing defects. And with these defects included, the structure that the z-hat invariants have is that of vector-valued quantum modular forms. Now, knowing this modular structure, then I want to discuss going to the other side, so taking tau to minus tau from the upper half plane to the lower half plane, briefly explaining also the relation to vertex operator algebras, and then discuss 2 approaches to performing this continuation based on resurgence and modularity. And from modularity, can already give you the preview that the defect invariants on the other side will be given by mock modular forms. And specifically, these will be presented as regularized indefinite theta functions, which in turn will give a connection to vertex operator algebras on the other side. So let me then start with the hidden modular symmetry that I discussed. So this is related to value representations of SL2Z that are constructed from a vector of Jacobi theta functions, two M of these, which span a vector which spans a 2M dimensional representation. Now from these, the value representations are constructed as sub-representations with a basis that is given by some linear combinations of the theta functions that entered the original vector. And these are defined by the action of a projector matrix. And the projector matrix is specified by the index and by K, which is a set of exact divisors of this index M, which is specified by the, well, in relation to the Z-hat invariant, is specified by the three-manifold. So the projectors, they are explicitly constructed in terms of a set of omega matrices. And the point is that the resulting basis vectors, they are given by us linear combinations of a subset of the theta functions that enter the original vector that we started with. Now that's quite a complicated way of saying everything. In a concrete example, if we go back to the sigma 237 example that I introduced, in this case, M was equal to 42. The set K, the subgroup of exact divisors, is given by these three integers. And applying the projector that I defined on the previous slide, we get this vector. And the point to observe here is that there are only three linearly independent combinations of theta functions, with the key observation that if a theta function appears in one of these, it will not appear in any of the others. And now comparing to the Z-hat invariant that I presented, in the case of sigma 237, we see that this is combination of the four, well, in this case, they are not the theta functions, they are the holomorphic Eichler integrals thereof, but they correspond exactly to the first entry of this vector. So here, the first question that I asked becomes transparent. The governing symmetry is given by this representation, but what about the other Weyl orbits that appear here? Because the Z-hat invariant, in this particular case for sigma 237, there is only one in the way it was defined. So this was the motivation to introduce the defect Z-hat invariants, where the defects refer to inserting, well, physically, they model the insertion of Wilson loops on links supported at the nodes of the plumbing graph. And concretely, what happens with regards to the definition of the Z-hat invariant is that the lattice summation gets shifted by the three integers that specify the Wilson loop, and the integrand gets multiplied by Laurent polynomials that are associated to, well, to each of the Wilson loops included, and depending on the node of the plumbing graph where these are included. So in terms of this, one thing that has to be, that we had to show is that with this modification, the newly defined invariant is still a topological invariant, and this is true because it is invariant under 3D Kirby moves, which act on the plumbing graph, which do not change the manifold. And now, to show you an example, if we return to the sigma 237 and we insert a Wilson loop on the link, which is at the node that I highlighted, if the weight is 0, then we have done nothing. So we just recovered the original invariant that I had on the previous slide. But if W3 associated to the link is equal to 1 or to 2, we get precisely the other two entries in the vector that I mentioned, so the other two val orbits. So in this way, we construct the set of z-hat invariants associated to the manifolds when including defects. We see that they form a vector-valued quantum modular form. Now, so this is just an example for where to associate the Wilson loop and what weight to give. In general, if for any other combination, the resulting invariant will still be in the linear span of these of the entries of the val representation. So now what we have shown as a general statement is that the defect invariants for general Britzkorn spheres specified by relatively co-prime P1, P2, P3, they span the components of SL2Z vector valued quantum modular forms, where the index M and the subgroup of the group of exact divisors K are specified by the manifold and nothing else. And then R star, these are determined by the weights of the defects. And now more generally, so this is the first statement is a theorem in general. For other types of manifolds that are cipher fibrations but not Britzkorn, there we have to do a numerical analysis, and we have extensive evidence that the same statement continues to hold.
May I ask in which sense they're invariant?
What do you mean?
I mean that it's defined in a non-invariant way. It depends on the plumbing graph, but probably you can check that it doesn't. But when you insert defects, it depends on
Well,
more.
the defects need to be preserved. Once you insert the Wilson loop, so here I glossed over this. So it is unchanged under 3D Kirby moves, but as long as these preserve the nodes at which the defects are supported. So that's what we check, and the proof just follows the original one for the invariant defined without defects. Is it okay if I continue?
Mm-hmm.
So,
Yeah.
so now the point is that having gone through this effort and defined these defect invariants, the relation to vertex operator algebras, logarithmic vertex operator algebras, comes through the fact that in all of these cases, the defect invariants, we find that they are proportional to a linear combination of false theta functions, where, like I said in the beginning, the index is fixed by the three manifold. And the false theta functions, they are identified with characters of the so-called 1, M singlet logarithmic vertex operator algebras. And so it is possible for all of these defects for all of these invariants with and without defects to consistently associate such a singlet log VOA to the three manifold, which has a 3-star plumbing graph, and therefore to the z-hat invariant. And now so far,
is it just a formal assignment?
Exactly. And one could also say it's not really that terribly impressive, because so far, if we're just looking at A1 theories, this could still be a coincidence because the false theta functions are quite simple. What makes it less of a coincidence is that if one goes to the higher rank invariants, which we have studied, there first of all, the type of quantum modular structure becomes much more involved because these become higher depth quantum modular forms. So the types of summations involved are far less transparent. And yet, even there, this identification continues to hold. So that is a non-trivial check. However, it is an absolutely very valid point that this is an experimental assignment. It's not a derivation. It doesn't give a proof or a way to show how from either 3D topology or from the supersymmetric quantum field theory, one finds these vertex operator algebras. But now, where this should come from is the physical perspective that I had highlighted in the beginning. It has this trimanifold with a boundary. So the expectation is that these vertex operator algebras, they actually live on the boundary of the 3D theory, or they should be related to those vertex operator algebras. So that's point one. And point two, the modules that appear should categorify the half index and the WRT invariant. Now, since it's almost half past, now let me talk about going to the other side. And there are various, sorry?
No, nothing.
So there are various perspectives on this. And this is also why I wanted to review in the beginning the nodes of this web of relation, this web of relations where these invariants have an interpretation. Because going to the other side, I said takes tau from the upper half plane to the lower half plane. And if we see at how this is interpreted, if we look at how this is interpreted in each of these settings, we see that it is quite a strange operation to perform. So if we start generally from the physics of 2D, 3D coupled systems, where we just have this Q-series expansion. Now, I told you that from the 3D SQFT point of view, there is an n equal to 2 theory on the cigar background. And there is 2D n equal to 0 to boundary condition. So there is an asymmetry between the chiral and anti-chiral part. And tau is here the complex structure parameter of the torus boundary. Now, what happens when taking tau to minus tau? From the point of view of the bulk 3D theory, this operation is fairly harmless because it just flips the signs of the Chern-Simons level in the Lagrangian description of the theory. But from the perspective of the boundary, this is a parity operation, so it is quite strange related to supersymmetrizing, desupersymmetrizing. Now, this doesn't imply much for calculational purposes, since also for the original invariants, it doesn't do much. But now if we switch to the quantum algebra node and the vertex operator algebra characters, here taking tau to minus tau replaces Q to Q inverse. So the Q series generated, they are divergent. And it's also very strange because it flips all of the conformal weights in the central charge. And then from the point of view of 3D topology, from the relation to the 3D Chern-Simons invariants, recall that I mentioned this limit where one takes a radial limit in tau and then a summation over A. So looking at the perturbative expansions, we see that the series expansions become oscillating if one takes k to minus k. From the integral form equation, the integral form of the Chern-Simons invariant, we also see that formally taking k to minus k, formally this is equivalent to reversing the orientation of the trimanifold. But what this implies is that if we started with manifolds that are weakly negative definite, the counterparts would be positive definite or weakly positive definite. But from the perspective of the integral formulation that defines the z-hat invariants, this also gives divergent Q series. So then that's why I was saying in the beginning, there was this thorny question of how to go to the other side. And then the supplementary question that my group transfer is how to find the analog of this connection of the arrow B between the 3D TQFT and the vertex operator algebra. So here, to go to the other side, there have been various attempts over the years. There have been some that focused on knot complements and using inverted Habiru series of rings, trying to use positive, negative versus positive surgery, and have had some degree of success. The issue being that they neither give insight into the modular structure of the resulting Q series, nor do they give reveal connection to vertex operator algebras. Now, what I wanted to spend a little bit more time on now is this resurgence approach that starts from WRT invariants, which is a paper that appeared last autumn, because this does provide a systematic computational approach. So here, the idea was to start from Q series, the Q series that were the original object, and construct dual Q series that are also convergent, with the condition that they have the nice integrality properties. So this goes back to the idea of having integer power, integer coefficients, because they are supposed to be counting functions even from a physical perspective, from the point of view of categorification. They also should have compatible asymptotic series expansions around Q equal to 1. So here, H bar or tau around 0. And one should be the analytic continuation of the other across the boundary. So the key object here that plays a role in this analysis are the resurgent transseries of Mordell-Borel class integrals, which have allowed to make some progress. Now, the idea was that the analytic continuation from H bar smaller than 0, which is tau in the upper half plane, to H bar smaller than 0, the analytic continuation of J, which here I should mention, the expression is valid for small H bar. There is an analogous one, which is valid for large values of H bar. Now, the analytic continuation can go two ways, and it gives two functions, J plus and minus. And from these, it is possible to extract two Q series. So a Q series, which is the real part, which is a series in e to the H bar, and a counterpart, which is Q tilde from the imaginary part. And note that Q and Q tilde are small in different regimes of H bar. So starting from these Mordell-Borel class integrals, it is possible in the analytic continuation in this direction to distinguish the resulting small and large Q series. And these are, with this approach, it was possible to extract false theta functions related to mock modular forms. And there is a nice example that is written out in this paper. Now, in the other direction, it gets more tricky, because there is not, the authors found that it is not possible to make this, how to say, the split between real and imaginary. The result is real. So how to distinguish the Q and Q tilde series, or their insight was that they should take an ansatz for the decomposition of this form into Q and Q tilde, which was inspired by what I showed on one of the first slides, is the composition of the Z-hat invariant into a perturbative contribution and a transseries into a contribution coming from the abelian Flat connection, and a contribution that comes from the transseries with non-abelian Flat connections. So taking this as an ansatz, what the authors did was perform a numerical fitting that allowed to generate order by order the coefficients of the Q series that appear on the right side. And there, in that way, go to the other side and verify the results in examples where this was possible, that they agreed with relations expected from mock theta functions. But now the downside of this approach so far is that it does not produce closed form functions for the series on the other side. It just provides a numerical way to compute these. And so from this approach, the vertex operator algebras, they are still a mystery. Now the counterpart with modularity, some of the requirements are similar. So the requirement is that the pairs of z-hat invariants associate the original one, the false invariants associated to weakly negative definite free manifolds, and the counterparts associated with the manifolds, the reverse orientation, they should form false mock pairs. Is there a question?
Do they form what?
False mock. So one is false and the other one should be a related mock modular form.
Mm-hmm.
So now the relation is that for mock modular forms, now these were defined as holomorphic functions with some weight, for which there exists a unique weight 2 minus k modular form, the shadow, such that the completion is modular but not holomorphic. And the shadow is given, and the completion is constructed with the non-holomorphic Cauchy integral of the shadow. And now there are compatible asymptotic series expansion between. So asymptotic series expansions in some small parameter t as tau approaches the rational line between the bounded part from the mock modular form, the non-holomorphic Eichler integral, and the holomorphic Eichler integral. So these have compatible asymptotic series expansions. And so from the point of view of modularity, the requirement is that these z-hat invariants should form a false mock pair with counterpart mock invariants, which have compatible asymptotic limits as Q approaches the boundary of the unit disk, and where the original false invariant is related to the holomorphic Eichler integral of the shadow of the mock counterpart. So now the canonical example, which is why I also started with the example of sigma 237, is that for mock modular forms, there are Ramanujan's order 7 mock theta functions, which have an expression in terms of Q-shifted factorial, and for which the shadows are given precisely by the 3 linear combinations of theta functions that we saw at the beginning of the seminar when looking at the Bell representations. So what we see is that the expectation based on modularity is that the original z-hat invariants should form false mock pairs with these order 7 mock theta functions of Ramanujan. And now, in the case that there is no Wilson loop included, so we're just looking at the top line, this identification was was proposed quite a few years ago and then subsequently proven using knot complements. So now we have an interpretation for the other mock theta functions. Now, because time is running very short, I'll skip the Apple-Lurch sums and show how to actually construct systematically these false mock pairs for a class of free manifolds. And that is what I announced in the beginning, this regularized indefinite theta functions. Because if we start with the convergent Q series that were defined, and we simply map Q to Q inverse, we get divergent Q series. And divergent Q series that are associated to indefinite lattices, they can be regularized. This was shown by Svegers more than 20 years ago, by restricting the summation to be not over the entire lattice, but simply over a cone, by introducing a regulator, which is zero outside of the cone, such that the resulting Q series is absolutely convergent. So now, given this insight, how to go from a divergent Q series to a regularized indefinite summation, the procedure for the Z hat invariance is to very well integrate over Z and send Q to Q inverse, but then multiply the resulting Q series by modular form, which makes the turns this into a lattice summation with an indefinite quadratic form, and then restrict the summation to be over a cone by introducing a regulator. And now the sum of the components, they are strictly dependent on the tree manifold. And the key to making this procedure work is to determine this cone summation, to determine the vectors, such that the shadow is compatible in the way we expected it or required it with this approach. So this is what we did. We found for a class of Priscorn spheres. We constructed the mock Z hat invariants as regularized indefinite theta functions with a precise combination for the regularization data given in terms of the data that specifies the manifold and an additional regulating factor. And what we have found is that the cone inside of the lattice depends only on the tree manifold. This is very important. It does not depend on the defects. The resulting Q series, they agree with where we could check with the expectation based on not complement calculations. And the defect invariants that we constructed in this way are in general mixed mock modular forms. For a restricted set, so when S and T are 2, 3, we get pure mock invariants. So the shadow coming from the C2 component vanishes. So this is a technical remark just because it's quite nice to see how this works out in practice. And then the very, very nice thing is that because the cone only depends on the tree manifold, not on the defect data, this allows us to construct cone vertex operator algebras that are associated to the mock invariants, so which have modules whose characters are given by these mock modular forms. So the cone VOAs, very briefly, they are defined as sub-vertex operator algebras of lattice VOAs by restricting to a cone. So this, in some ways, it parallels the construction of the log VOAs that are also defined from lattice VOA by a restriction. And I guess to say just 2 more points, the lattice that we start is just the original one from the summation. So now the cone is closed under addition and it contains the origin, and the resulting vertex subalgebra that we construct starting from this cone is a vertex operator algebra if the cone is positive definite. The cone is generated by vectors, direction vectors that are orthogonal to the ones that specified the cone, C1, C2. And so we find we give a prescription to construct these twisted modules and trace, which when evaluated, is equal to the mock invariants. Now I see my time has run out. So to come back to the context, to zoom back out, what we have seen is that, well, going back to the questions that I had asked in the beginning, the structure of the z-hat invariant, z-hat invariance is that of vector-valued quantum modular forms. And using this knowledge about the modularity to go to the other side, we are able, at least for a class of manifolds, to give a proposal for defining the mock invariants and then using the specific formulation as regularized indefinite theta functions to then construct corresponding vertex operator algebras. And now it's still an open field because the types of manifolds that we have investigated are still relatively special, which is not quite satisfactory. There was this question in the beginning about how to associate or understand the vertex operator algebras, and the relation ideally should be understood directly from the 3D SQFT. And there is this big question, which is far from obvious at the moment, is how the two methods, what is the interplay between the resurgence approach and the one using modularity, because the resurgence did not use any input or requirement or constraint from modularity. And yet, in many results, modular structures were emergent. So that is where I think it's a nice direction for further study.
Thank you very much. Any question?
This latest in latest VOAs, how they related to M3 to your manifold?
Sorry, it's okay if I stop sharing so that I also see the room.
Yeah.
Okay.
If you have a lattice with a bilinear form in this VOA story, yeah? This lattice, is it related somehow to the homology of your M3, or maybe some
So no, in the case no, in the case of on the false side, when looking at the log VOAs, this is just the Z, but rescaled by M, what appears as the index of the theta functions, or rather it's square root of M that appears in the rescaling. And more generally, if you go to higher rank, is the root lattice of the it's a rescaled version of the root lattice that appears in the that enters the definition of the invariants.
And do you remember in the resurgence approach that you describe what is the structure of the singularity, or like whether they can really compute the Stokes, they have some general result in terms of Stokes constant or something like that? Or is purely proving that this series, if I start with this indefinite theta, I get something, I mean, they are resurgent, okay, but how much do we know about the structure?
So I think not much is known beyond the fact that using these Mordell-Borel class integrals, they see that if they do the analytic continuation and then impose, like that is the crucial part, impose this ansatz for the decomposition that is motivated by the structure of the false z-hat invariants, then order by order they are able to fix coefficients, and that's it.
Okay.
But again, I'm not an author, so this is my understanding of the paper. But it is very curious how modular, what should be the interplay, because these two methods combined, so putting the two together, requiring modularity, and using this resurgence approach together, they could be quite powerful, and they would have nice implications, not just for the z-hat invariants themselves, but for VOAs.
I mean, in the case of just torus knot, we see how the two somehow are related, say, but okay, that's just a classic example.
Exactly.
And we can also conjecture for hyperbolic knot, I would say. Between, I mean, the fact that they are quantum modular form, but in a sense that the cocycle can be expressed as Laplace transform. The asymptotic
Right.
series.
Mm-hmm.
But yeah.
Exactly. So there's a lot to discuss in this direction.
Yeah. Are there questions from Zoom now? Or? Georgian?
There's no.
Okay. So if there are no other questions, thank you, Ioana.
Thank you very much for the invitation.
Thank you. Bye.
Have a nice afternoon.
Thank you.